Cool. Well, thank you for inviting me. As you said, I'm going to be talking about superconductivity this evening. And in fact, what I thought I should talk about, as well as superconductivity, because I was also expecting a few more younger minds here, or younger in body as well as in mind, shall we say, was a little bit about what research is about. Because I think that's sort of important for them to see that science isn't a fixed thing. And so there's obviously a lot of the history that takes us to where we are now, but really it was not just telling them about superconductivity, but telling them a little bit about what it is we do every day and what we get to play with and what's exciting. Okay, so in first of all telling you what superconductivity is, it's easiest to tell you what superconductivity isn't. And so superconductivity isn't what makes your toaster glow and get hot and makes your toast brown. So a toaster gets hot because we're passing a current through the wire, and there's some resistance to that current, or the lights come on, and that's dissipating energy. So we all know about very simple circuits. We know how to light a bulb with a battery, and we can connect the battery, and as soon as we complete the circuit, current is flowing. That's moving charge, and the weak link in this flow is the filament in the bulb, and that's where you have the most friction, if you like, to the flow of electricity, and that generates heat, and more desirably, that also generates light. Okay, so superconductivity is the exact opposite of this in the sense that it's something that doesn't have a resistance. So over 100 years ago now, this guy Kamerlingh Onnes, who was working in Holland, in Leiden, discovered that when he made some metals very, very cold, their resistance, so this is temperature here, room temperatures through this wall over here somewhere, this is 4 Kelvin, which is minus 452 Fahrenheit, the resistance of the metal disappeared. It suddenly dropped to 0. And he did this in 1911, and in 1913 this was recognized with a Nobel Prize in Physics. Okay, so this immediately asked this sort of rather big picture motivational question, which is if our national power grid has about 6% of its use is just lost in transmission, in these resistive losses, and this isn't even taking into account the fact that my computer's sat here humming away, getting rather warm while I'm giving this talk. And the country uses, 4,000 billion kilowatt hours. We lose enough energy just in transmitting the electricity across the country to boil something like 2 trillion kettles of water a year. And so, the big picture question, which doesn't necessarily motivate me, but it motivates people that fund the sort of research that we want to do, is what if we knew how to take one of these materials and actually design that material so that it would carry current without loss at room temperature? We didn't have to cool it down to very low temperatures. Okay, so Bob made me promise not to go into great depths with the theory here, but I think that what I wanted to point out was that it took of the order of 50 years before there were enough experiments done so that some theorists could come up with a model that enabled us to explain and understand superconductivity that's happening at these very low temperatures. And the details are that it turns out that it's the sound waves in the crystal, in the material, in the metal that's superconducting, that's actually causing the electrons that carry the current to interact with each other, and that gives rise to this superconducting state. However, this theory also tells you that it's really only limited to very low temperatures. And so that starts to ask the question, what other interactions can you have in a material that might give rise to superconductivity that might work at higher temperatures? And so that's very much sort of the motivation of what we do. We do material science. We use high magnetic fields to do material science. And so when I talk about interactions, I think this is sort of a rather nice picture to think about, is that when we go for a hike in the hills and we're walking along by ourselves, our progress is very much governed by our energy. Our momentum stays the same. It's governed by us. If we walk down a crowded street, there's a very, very different path to our progress. It depends on the sort of the collective motion of the crowd. If the entire crowd is trying to get in the tube station over here, we're going to be sucked this way. Or, you know, if we bump into 30 people between here and here, our progress is going to be much slower. And so that's, on a very big picture level, what I mean by interactions in a material is that we're not thinking about how electrons perhaps behave as individuals, but how this collective behavior might give rise to materials' properties. Okay, so coming up in temperature, and we'll get to some of the demos very shortly, in the early or mid-80s, supposedly high-temperature superconductors were discovered. So these are certainly much higher temperature superconductors, and what I've got here is a graph of the temperature at which these superconductors or these materials superconduct as a function of time. And right around here in about 86, suddenly we discovered some, not me personally, the scientific community, discovered that there were materials that weren't good traditional metals that in fact superconducted. And they're ceramic materials, they're copper oxide materials. When I say ceramic, I mean they're materials a bit like your coffee cup, in that they're not necessarily good metals. And this was actually quite intriguing that in fact they're more closely related to magnetic insulators than they are good metals. And so over the past however many years since then, the superconducting temperature has sort of increased. And it's increased basically by following this recipe and sort of cooking and making different materials. But we don't have a good theoretical understanding or basis upon which to say, we understand how this works. Can we design one that is at room temperature? And again, bear in mind, room temperature is up here somewhere around the blue line at 300 Kelvin. Okay, so I've told you that basically what a superconductor is. It's a material that doesn't have any resistance. It conducts electricity without loss. And I've told you that some of these materials that look like they're promising for getting maybe halfway to room temperature have interesting magnetic properties. So what about the magnetic properties of superconductors? Okay, so when we talk about magnetism, we're not just talking about Wile E. Coyote's Acme magnet here sucking onto magnetic things, not just me picking up a paperclip with some strong magnets. We're talking about electromagnetism and the fact that electricity and magnetism are really quite tightly intertwined. And so for the next couple of slides, and we've got a couple of nice demos for this, we'll show you what we mean by electromagnetism, and this will show you how we create magnetic fields in the lab. So going way back to the 1800s, Ampere, who the amp or the unit of current is named after, discovered that electricity in motion, or a current, creates a magnetic field. So if I toggle backwards and forwards between these slides, this is a cartoon of a coil of wire. And when we pass a current through a coil of wire, it creates a magnetic field shown by the green lines that look very much like the magnetic field from a bar magnet. So if I kind of step out the way, oh no, please.
So this is just a nail, and we took a piece of insulated wire and wrapped it around the nail. And as you can see, it doesn't pick up a paper clip. So, and then all we're going to do is attach it to the battery and drive current through the coil, and then it picks it up.
Wow.
So it's that easy to make a magnet.
So when I'm talking about magnets, I'm probably interchangeably talking about an electromagnet, and that's probably what I'm talking about most of the time. This is the sort of gauge wire we use for some of our big research magnets up in Los Alamos for doing material science. You can see it's a much heftier coil to carry much more current. There's normally a lot more reinforcing material around this, and I'll explain some of that later. But that's the first takeaway message, is that a current or a moving electrical charge produces magnetism. Okay, so the next point to take is to do with Michael Faraday, who's also very prolific in this era, and that's that he discovered that the motion of magnets can produce electricity. And so one way to show you this is what we have here is another coil. This is very much like this, slightly different geometry. It's shorter and fatter. And we have magnets, so these will pick up paper clips by themselves. They're permanent magnets. And when Kim moves it in and out of the coil, you can see a little meter here that's measuring a current starts twitching around. And what you'll see, moreover, and what's interesting to note, is that when the magnet is still, even though it's in the coil, the needle isn't moving. So it's the moving magnetic field that's inducing a current in the nearby conductor. Okay? So there's one more demonstration that sort of goes with that, and that is if we take one of these Nice strong magnet. Oh, Kim's got a better one here. So if we take one of these nice strong magnets, we can do a demo to show magnets in motion and how they induce currents in nearby conductors. So we've got a whole set of slides here. I can put it on here and let it slide down. This happens to be a piece of plastic, not a very good conductor, all the way to copper, as you might suspect, at the other end, which is a much better conductor. So any guesses from the audience what's going to happen? And I know some of you have seen this many times before. What's going to happen when I try and slide the magnet down the different materials? Now, bear in mind, none of these are magnetic materials, so the magnet doesn't actually stick to any of these. Come on, a little bit of audience participation. Is it going to slide faster? Slide slower? Not slide? Stick? Slower. Okay. Stick on some. Okay. So I like the guess slower because I know the answer. The question is why? Okay, so let's just do this and I'll make you count. So let's count on the first one how long it takes. You ready? One. I'm not fast enough for that one. Okay, so this looks like it's a bit of stainless steel, non-magnetic stainless. So this is a conductor, but not a particularly good conductor. So did we get one? Should we try again, get some statistics for this one? Ready? Mate, can we tell it's slower than that one? Maybe, I don't know. Okay, now we've got some brass. 1, 2, 3. Okay, aluminum, as you might say. 1, 2, 3, 4. Cool, huh? So that's aluminum, so that's a slightly better metal. And then copper, which is a pretty good metal. That's what most of the wiring in our homes, unless perhaps you've got a Vietnam-era house up in Los Alamos. So there you can see that's going much, much slower. So I love this demonstration because this is something that, as a kid playing with magnets, I never came across. You play with magnets and you know about magnets sticking to magnetic metals. You know about magnets sticking to other magnets and having north and south poles. But this idea of a moving or a changing magnetic field inducing a current in a nearby conductor, and that current itself having a magnetic field that's retarding the motion of the magnet. I love this demonstration. So you guys can come up and play with this at the end some more. So that was Michael Faraday. He had the idea that the motion of magnets can produce electricity. There's one more curious thing, and there's a really quite nice demonstration that we came up with this week, actually, to show this. And that's that the Lorentz really summed this up by saying that there's this nice relationship, or this very convenient geometrical relationship between the direction of the magnetic field, the currents, and the force on the current that's in the magnetic field. That's the word I'm looking for. Okay, and the fact that these are all are perpendicular to each other. So a moving charge or a current in a wire perpendicular to a magnetic field experiences a force perpendicular to that. So the demonstration is, and if Kim's got some magnets, and so these are magnets. They stick to these magnets. Oh, sorry, and they're pretty strong magnets, as you can see. So we don't want to pinch our fingers in them. And so what we're going to do is we're going to stick a battery on top so that we can drive a current. And it's convenient that these magnets are metallic, because we're going to use that to make contact to one end of our electrode. And then the next ingredient, you can use that. The next ingredient is just a piece of copper wire, as you might find the ground wire in your home, bent into an M shape. So there's nothing particularly helical about that. And what you'll see is when we put it on top of the battery, it's completing the circuit. So current is flowing from the top of the battery, and it's going back into the bottom of the battery by making contact with the magnet. Until it gets too fast and flies off. So why have I shown this in combination with this idea that everything is perpendicular? Well, again, I've drawn the field lines on here. So the field lines are coming, and magnetic field lines always want to eat their own tails. So they come out the top of the magnet and go back in the bottom. But what you can see here is that they're perpendicular to the direction of the current flow in the wire around the outside. So on this side, you've got the current going perpendicular to the magnetic field, causing a force that's coming towards you. And on this side, you've got exactly the opposite situation. The current going down, perpendicular to this magnetic field, and a force going away from you. And so the net result is you've just built a little electric motor. So what do you expect to happen if we reverse the direction of the magnetic field? Going to spin the other way. Let's see if this... No? Spin the same way. Other way? Everyone's got their left and right hand rules, and it spins the other way. So I love this because it's just so simple to show, you know. Okay, so, all right, so in a couple of slides and a few minutes, we've shown that electricity and magnetism basically give you all the ingredients of the Industrial Revolution. That motion plus magnets can produce electricity, and in fact, we can, you can take one of these little generators and we can wind it and we can light a light bulb with it. And we've shown that we can make a motor and that electricity and magnets can produce motion, and now we have a proliferation of electric cars around town. Okay, so any talk that involves electromagnetism wouldn't be complete without acknowledging Maxwell. It isn't because I want you to look at any of these equations, only to note that Maxwell unified all of this in 4 very eloquent equations. And what's important to note with this is that basically everything we experience is electromagnetism. The chemical bonds that hold us together, the fact that I can touch the table, the fact that I can see light in this room, is all due to electromagnetism. And I think that's kind of, as a big overarching principle of the fact that we use high magnetic fields and we use electromagnetism to do material science, we often forget that that's sort of everything we experience. Okay, so now we should go back to superconductivity. And before we do, there's another demonstration that's very similar to this one that I love because, again, it's magnets not sticking to copper and yet falling slowly through a copper tube. So let's...
This is just a magnet, and this is the copper tube.
You guys have got to count again. Oh. So
Let's count along.
Yeah, no, you make them count.
Okay, ready? 1, 2, 3, 4, 5, 6. Ready?
So I was just looking to see if we had a second tube. I was going to pass it around and let you guys drop it, because one of the really nice things is that when you drop it, so you don't hear anything when it drops. So the magnet's not rattling down the inside of the tube. In fact, the magnetic field, the currents that it's inducing in the tube as it falls, are actually keeping it away from the walls of the tube. What Kim's going to do now is what we have here is a dewar, which is basically like a thermos flask of liquid nitrogen, liquid air. So just to show you that that's liquid air, while Kim is going to take this piece of metal and cool it down, what happens? Oh, here's the little bucket. So here's a balloon we blew up earlier, just air from my lungs, probably a little bit more carbon dioxide than usual, but mainly nitrogen. And I'm going to put it into the liquid nitrogen, and what you'll see is that I'm liquefying the air in the balloon. So this bucket just basically contains liquid air. And then when I take it out, as it warms up, if it doesn't burst, it should reinflate itself, maybe. There you go. Okay. So yeah, that's very cool. So when we liquefy air, it contracts nearly 1,000 times. And so basically the same volume of, or the same amount of air is in there, the same number of air molecules, but its volume is collapsing because we're liquefying it. So this is just liquid air. Kim's dangling the copper tube in liquid air. And the reason we're doing this is that metals become better conductors when you get them cold. Now, this isn't going to become a superconductor, but it's going to become a better conductor, and then we can do the experiment by dropping the magnet again and counting, and we'll see if this drops even slower. So,
ready?
Here we go.
1, 2, 3, 4, 5.
It's stuck.
6, 7, 8,
I don't know.
9, 10, 11.
So,
I was like, it's really stuck.
I know, it could be stuck. So, as the conductivity of the tube gets better, the moving magnetic field induces more current, or there's less dissipation, and the magnet falls slower. Okay, so what would happen if this was a superconductor? What if this was a superconducting tube and I put a magnet in the top? How long would it take to fall through? It's rather cold, actually. By frostbite. Yes, you didn't see that on the film. Don't try this at home, children. So come on, answers from the audience. What would happen if we... It would never go through, I heard? It's a pretty reasonable guess. So what Kim has over here is, and maybe she can point to them so I'm not stepping in front of the projector.
Just something holding some liquid nitrogen to cool down a superconductor. This little glass dish is just holding liquid nitrogen, and inside there is a big piece of superconductor.
Yeah. So these black squares are some of this ceramic copper oxide superconductor we were talking about.
The ones that had the highest TCs, halfway to room temperature.
Yeah. So the TC of this, or the superconducting transition temperature, is above the temperature of the liquid air. So now they're superconductors. And this one we have cooled down without any magnetic fields near it. So Kim's going to do the equivalent of trying to drop the magnet past the copper, or into the copper tube. But now with a superconductor. So let's see what happens. Oh, that was pretty cool. I like the way it bounced off. That repels it. I really like that. So, okay, so what's happening here? So here I've drawn a cartoon, and I've drawn it with two magnets to draw some field lines going between them. And here's a piece of superconductor that my animation shows it turns on to being a superconductor. And as we cool down that superconductor, it wants to expel the magnetic flux lines from inside it. It wants to get rid of the magnetic fields inside it. And so when we try and put a magnet near it, it acts as like the perfect opposite magnetic pole and pushes that away. And that's why it's unstable and it goes flying off, because it's like putting two magnetic, trying to balance a north pole on a north pole. It always wants to flip over and it's unstable. Okay, so this is sort of a cartoon of that, and that's saying that basically because we can drive currents without any loss, as this material goes superconducting, there's a current that can flow around the outside, and that current can exclude the magnetic field from the inside of the material. Okay, so there's another piece of superconductor, very similar to that, sat on this side of the table. In fact, there's no real difference between the two. But this time, we've cooled it down with the magnet balanced just above the magnet balanced just above the superconductor. And what we're going to see this time is that instead of the magnetic field lines being pushed out of the superconductor and it bouncing away, it's actually going to trap those magnetic field lines in place. And so if Kim would like to take this piece of foam away.
So we cooled it down, we had a piece of foam in between the superconductor and the magnet.
Don't burn yourself. And what you see there is now this time it's the most equivalent to what we guessed at for the tube, is that if we drop it, it just hovers there and never falls through. So there's enough people, small enough crowd in the room that if you guys want to come up and look, you can see that I can put something underneath. I can try and, I've got to get it right. See, Kim has the magic touch. There you go. But basically it wants to sit there and levitate above the magnetic field. And the difference now is that because this is a big piece of superconductor and the particular type of superconductor, as we cooled it down, some of these, instead of the current that screens the magnetic field from the bulk flowing around the edge, there are these little places where we pin it as tubes through the middle. We call them flux quantum, but basically it's this supercurrent flowing around, screening the magnetic field from the bulk, but trapping it as lines going through, and we get this levitating superconductor. So this immediately suggests another industrial application of superconductivity, and that's that you can make a levitating train. And so in fact the Japanese have been investing quite a lot of money in this, and in looking for a nice picture for this talk, I found that last year they had their first public tests of their 300+ mile an hour magnetic levitating train that has cut a commute down to something like 40 minutes from 2 hours. But this is billions of dollars investment. And again, the problem with this technology is that in order to make this levitate, we have to keep these superconductors at the temperature of liquid air. And so again, if we can make one that works at room temperature, you can think about removing all these frictional losses from transport. Okay, so we've told you a little bit about superconductivity, and we've obviously played with a lot of magnetism things. Now we're going to tell you a little bit about how we use magnetic fields to study the properties of superconductors. So the magnets that we've been using today are neodymium iron boride magnets. They're pretty much the strongest permanent magnets you can buy or you can make. We call them rare earth magnets. And you can see the effect that has on the superconductor is to kind of barely tickle it. The superconductor sits there still superconducting, maybe with a little bit of flux pinned inside. If we want to significantly affect the superconductivity, we're going to need a much stronger magnetic field. And so just to put the strength of magnetic, so I'll use the term Tesla, that's the unit for magnetic field, like amps is the unit of current. And so the Earth's magnetic field is surprisingly weedy down here at some small fraction of a Tesla. Your typical kids' refrigerator magnets are nowhere near as strong as this because you don't want your kids pinching their fingers. And they're something like, you know, a couple of, or getting on for maybe 1/100th of a Tesla. This is probably getting on for a significant fraction of a Tesla, maybe 1/10th of a Tesla right at the surface of this. So you don't want to put it on your cell phone or your credit cards or your something else. It wouldn't be the first time I've swiped a magnetic badge or something. You know, a junkyard magnet can pick up a car with 1 or 2 Tesla. And so the research magnets we're going to be talking about are 20 Tesla or greatly in excess of that. So we're making a significant change to the superconductor we're trying to study. Okay, so what's the problem? And you probably already guessed this, is that making big electromagnets requires lots of current, and lots of current has lots of dissipation, just like the light bulb. And so here's a picture of me from a couple of years ago, stood on top of the world's largest DC magnetic field. This is a 45 Tesla magnet. By DC, I mean this is something we can turn on and leave it on for several hours at a time while we do our experiment. The problem is, because it consumes something like 30 megawatts, this is a significant fraction of the state capital in Florida's power consumption, we have to pump something like 40 liters of chilled water a second through this magnet to stop it melting. And so this whole magnet is several stories tall, mostly taken up by the cooling system. And here you can see some guys underneath it. The magnet coils are now plates with lots of little holes in. That's where you're pumping the water through to stop it melting. And so the challenge is, how do you take that heat out? And so 45 Tesla is, at the moment, is the technological limit for doing that. And that actually involves a combination of normal wire and superconducting wire to try and make the largest magnetic fields possible. So our solution in Los Alamos, so this is our sister lab in Florida, our solution in Los Alamos is we make very big magnetic fields, but we only make them for a very short period of time. So we turn the current on, and this is my cartoon here, is that instead of connecting it to a large DC supply, I've charged a capacitor bank up to some high voltage. This is just like a battery. I've stored some charge. And when I close the switch, the current flows through the coil. It's like this. It's made of some of the world's strongest and best conductor. It has some of the world's strongest reinforcing materials holding it together. And we create a very strong magnetic field, but only for a fraction of a second. So we have the challenge of making our experiments work in only a few milliseconds, and sometimes only microseconds. Okay, so what's the problem we have in just going higher and higher in magnetic field? And that's that strong magnets produce really big forces. So going back to this idea of this Lorentz force, this left and right hand rule, and to put this into context, James Cameron was clearly very brave to get in his little solo submarine and go to the bottom of the Marianas Trench, was it 2 years ago now maybe? But the pressure at the bottom of the Marianas Trench, so at the bottom of most of the ocean, I've said it's 6,000 psi. It's about 3 times that depth at the bottom of the Marianas Trench. So let's give them the benefit of the doubt and say it's 20,000 psi. In some of our research pulse magnets, this is an 80 Tesla magnet, and as you can see, it doesn't look very healthy. We're reaching something like 10 times the pressure to hold this magnet together. So now our challenge is not only stopping the magnet melting by making the pulse short so that we can heat it up for a short period to then let it cool for an hour before we repeat the experiment, but we've got to hold it together against these very, very strong forces. And so one way we do that, and just to show you the sort of devastation we can cause when this goes wrong, all of our pulse magnets eventually fail. This looks to me like the scene in Alien where the thing has come out the stomach. You've got the middle of the magnet has ripped itself out the side. That magnet and this magnet use of the order of 1 megajoule of energy. That's about the amount of energy you get from eating a decent-sized Snickers bar. That's about the amount of energy that you will expend if you hike from here to the top of the ski area. That probably takes me an hour or two. So I can burn, as a human being, I'm a pretty energetic thing, I can burn a megajoule in about an hour. If I was on the Tour de France, I could probably do that in about 10 minutes. We do this in a fraction of a second. So when things go wrong, you go from something like this is about a foot, to something that looks like this, a box of rubber. It's like setting a stick of dynamite off. So paradoxically, if we want to go higher in fields, we actually want more energy. And the reason we want more energy is we want to distribute these forces over more and more reinforcing shells. It's a bit like the reason James Cameron's submarine needs very thick walls. And so this is a picture of me, and it's a bit of a joke picture. We photoshopped it to look like there's a refrigerator stuck to the side of the magnet rather than a magnet on a refrigerator. But this is the insides and the reinforcing shells of our 100 Tesla magnet. And so if I click, this is the magnet that in March 2012, we set the world record for producing a non-destructive magnetic field, meaning the thing didn't blow itself apart and is in bits, and we're still using it today to do research. And so inside all this reinforcing material are layers and layers, like Russian dolls, of coils like this. The outer one is about 4-foot diameter. The inside is about a centimeter diameter. Everything else are turns and turns of copper. And we put a lot of energy. This is now 140 megajoules of energy. So this whole building is evacuated when we do this, because eventually something will go wrong with this magnet. The key is how much science can we do between now and something going wrong. To power this, we don't have a capacitor bank. That would be a very, very large capacitor bank. So a 4 megajoule capacitor bank is about the size of this room. We now need several hundred megajoules of energy. So we have a motor generator. This is actually Rebecca stood in front of this. So you can see this is an industrial scale piece of apparatus. This came from the Tennessee Valley River Authority when they didn't commission a nuclear power plant back in the 80s. It came up to Los Alamos for a different purpose, and we now use it to produce magnetic fields. If I come over here and click on the little speaker, I think it will play the sound of the magnet. So this magnet, if you look at the graph at the bottom, this is the magnetic field against time. You can see it takes about 2 seconds total, with the kick that takes us up to this world record field only taking a few milliseconds on the top. So this is where we're trying to do our science, is in the top here. So if let me see if this works. Where's the mouse? Let's try again from the beginning. Maybe it didn't. So that sort of Banshee Godzilla-esque scream is the fact that we're taking an AC current source, the generator. So how does this work, actually? Let me just, do you want to, yeah, while I'm talking, Kim can share. So what we've got here is basically a small version of a motor generator. It's just like the battery motor. And so actually, first, why don't you connect it to the battery and show that it works like a motor. So if we connect this to a battery, the crank is, I hope it's going to turn. The battery's got enough oomph in it. There you go. So it acts like a motor. So what we do is we spin this up from the grid, and we have our own little substation, and this thing spins. And we get it spinning really fast, about 1,800 RPM, and it's storing a lot of energy. And then while it's spinning, it's got this inertial energy. We disconnect it from the grid, so we're no longer accelerating it, and we connect it to the magnet. In this case, we're using the bulb. And as it spins, it dumps its rotational energy into a current and a magnetic field. Now, the reason it sounds like this is it's actually an AC motor, and so we have to rectify something, and there's a ripple. And that ripple happens to be at that frequency, and so the magnet itself, this big thing I was stood next to, is acting like a microphone. And that's why the thing sounds a bit like Godzilla. So a little bit of random trivia there. So to emphasize what we use it for, we do high magnetic field measurements. And I told you that the inside of the magnet is about a centimeter diameter bore. So we need a very long stick that's less than a centimeter size to put our sample on. We call this a probe. This is a 1/4 inch across. And what you can see is that we've got many, many different materials, we call them samples, that we're going to measure their properties in high magnetic fields. And so this always sort of amazes me that you've got this contrast between this scale of a generator that's a warehouse size. You've got a magnet that's much bigger than me. We've got scary amounts of energy. And at the end of the day, we're measuring a sample that you can't necessarily see with the naked eye. This sample here is about 100 microns across. These wires aren't much thicker than a human hair. And we're using all this to try and understand the behavior of this material. So again, coming back to this slide about interactions, we're talking about, we're trying to understand, at least for the point of view of a superconductor, is how in these materials where the conductivity, the way the electrons carry current, isn't governed by the individual electrons, but by this collective behavior. So the question that I'm going to now try and answer is how we're using high magnetic fields to answer this question, to understand these correlations. And so I want to remind you something about quantum mechanics that you may well have heard before, or you may well not have. And so I'll ask you the question, when you look at this picture, what do you see? Do you see the particle, or do you see the wave? And I think perhaps you might argue that in any second now, the particle is going to become part of the wave and maybe eternally indistinguishable from the two. But the point I'm trying to make here is that quantum mechanics says that on a very small scale, on the scale of an individual electron, that things behave both like a particle and like a wave. Okay? And so one example of that is light. Light behaves, we often think of it like a wave. We can also think of it like a particle. And so I'd ask you, why do we see a rainbow? This is oil on the surface of a puddle. Why do we see the rainbow on the surface of the puddle? Any answers? Any guesses? The light reflecting. So the light's reflecting and it's picking particular colors. And so let me kind of give you the answer. And so yes, it's reflecting. It's picking particular colors depending on how thick the oil is at any given point. And what it's doing is the light is bouncing backwards and forwards inside the layer of the oil. And depending upon how thick the oil is relative to the wavelength of light, that wave either interferes with itself constructively or destructively. And so here in my rather exaggerated cartoon, I've drawn it so that the red is being interfered constructively and the green and the yellowy colors are being interfered destructively. And so in principle, you can either measure the thickness of the oil by knowing the wavelength of light and what color is being reflected, or conversely, you might say you could measure the wavelength of light by knowing the thickness of oil on the puddle. Okay, so where am I going with this in magnetic fields? So again, remember we have this demonstration that a moving charge in a magnetic field wants to experience a force and go round in a circle. So that's exactly what happens to the electrons in a material. They're all zipping around, and in a high enough magnetic field, they're going around in circles. If we make that magnetic field high enough, these are quantum mechanical objects, they're going to see their own tail. They're going to start to interfere with themselves. And that's exactly what this is here. And that's showing that this is the resistance and this is magnetic field. And it doesn't start at zero, unfortunately, this graph. And so what you're seeing is there's no resistivity. This is a superconductor. At some magnetic field above 20 Tesla, we start to destroy the superconductivity and we suddenly get some finite dissipation. There's a resistance here. As we can continue to increase the magnetic field, we get these oscillations, which are basically, as you make the electron go around in tighter and tighter circles, just like the light bouncing off the puddle, it starts to interfere with itself. And so we can use this to tell us how the electron is moving. And what we can use it to say is basically, how heavy does the electron appear? What's its effective mass? And that's saying that when I walk down a crowded street, one analogy is I effectively feel much heavier because I'm bumping into everyone on that street as I go than I would if I'm walking across an empty field. And so we've immediately got a connection between these correlations, these interactions between the electrons, the fact that they behave as a collective, and this use of a magnetic field to cause these interference effects in which we can measure this effective mass. Okay, so what we're going to do is use that for high magnetic fields. And what I've done here is this is a picture of one of our postdocs, and I included it really just to show that the physicists today don't quite have the same class as the the Maxwells and the Lorentzes of the past. But what we're going to do is we're going to use these oscillations as a measure of the effective mass of the electron. And what we're going to do is we're going to correlate that with the strength of superconductivity. So in these ceramic materials, depending how much you expose them to oxygen, you can tune what temperature the superconductivity occurs at. And so what you've got here is the best superconductivity clearly above the temperature of liquid air, around 77 Kelvin, but this depends on how much oxygen content there is. If we do this experiment and we extract this effective mass of the electrons, and we track this with the superconductivity, on this axis we've got the mass. Here it looks like it's got a mass of about 1, going up to more than 3. The mass is heaviest where the superconductivity is most robust. And so this is immediately telling us that we're probing the relevant interactions that are giving rise to superconductivity. Okay. So, say again, sorry? Hole doping. So hole doping is basically how much you've exposed it to oxygen. You're taking a material that wants to be a ceramic, a bit like a coffee cup, and you're tweaking it a little bit away from there by chemically, and you're making it a metal, but you're not making it a very good metal. And this metal, depending on, over here, when we haven't done anything to it, it's an antiferromagnetic insulator. To all intents and purposes, it's basically like your coffee cup, it's a ceramic. As you deplete this with oxygen, you suddenly start to become more and more metallic. Over here, you would be a good metal, but between being a really good insulator and a really good metal, you get this kind of funky metal, and at low temperature, that turns into a superconductor. And so what we're trying to correlate is how are these interactions related to the superconductivity? And this is really what I'm showing you here, is that this effective mass of the electron is highest where the superconductivity is strongest. Okay, so does this give us a theory of superconductivity? No, but it gives us another sort of key piece of understanding in terms of building a theory of superconductivity. So it's been almost 30 years now since the discovery of these cuprate, these ceramic superconductors, and we still don't have a theory. Bear in mind, it was nearly 50 years between Camerlinghonor's discovering superconductivity in the first place and a theory describing how sound waves lead to superconductivity, and a lot of very informative experiments in the meantime. And so maybe this is the problem for the next generation of young scientists that might be in the audience. But that's where we are, is that this really isn't a solved problem. But hopefully this has given you a taste of some of the things we do with high magnetic fields. We're trying to understand these material properties. We're trying to understand how they give rise to these interesting states that might be technologically relevant, like a superconductor or a magnetic material that might be in the hard drive in your computer, or you name it. So thank you very much for your attention. There's lots of things if you want to come and play. I don't know how much time we've got. I've probably been talking for way too long. Well, that's 42 minutes. That was not bad. I can. So I stuck some slides at the end to do with how when things go wrong, they can go very wrong. So if people have got questions, we can talk about how sometimes we do want to blow things up. Sometimes they happen by accident. I think it might be more fun if you guys want to come and play with stuff. I think that would be cool. Be careful if you're playing with the liquid nitrogen. And please ask me more questions.
How successful is the Japanese trade?
The fact that they've got something that is commercial,
Yeah.
I think that's pretty successful. This is so there's some systems in Europe and in Germany where they've got test tracks, and they'll build things and they'll use them over 5-10 kilometers. But I think Japan has really invested, and I think this is a multi-billion-dollar investment to put in something like 40 kilometers. No, I think what I read was it's dropped that commute to a 40-minute commute at 300 miles an hour. So that tells you that this isn't like some little test thing across Santa Fe. They're actually making serious investment. But again, most of this is me looking at stuff that resonate with you guys for trying to describe sort of the real-world application of this. In many ways, there are so many potential applications of the materials we're looking at that we can't even guess at. So, these big industrial scale carrying current without loss, making a train that hasn't got friction, is kind of easy to picture. Some of the things like how it might involve a superconducting computer that can solve quantum algorithms and crack codes, I can't even get my head around that. So explaining that to you guys, or the innards of my computer, or why it might be a much faster switch, why your laptop won't cook your lap at night, we can only guess. And I think at some level, we're foolish to be too predictive, because that's not what research is about. Unless you're talking to a funding agent, and then we're going to solve the ills of the world. So.
Are there any other questions?
Yeah, okay.
Some slides back, you had the encasement where the tube in the middle was like 1 centimeter.
Yeah.
With further use, does that encasement or closure weaken?
Yes, at some level. So actually, so let me describe this in a little bit more. So if I go back to this slide, what you're looking at the outside is the encasement, but this is basically about 1 inch of the world's strongest steel. So this, believe it or not, at one point was a continuous loop of steel. A failed magnetic detonation, if you like, inside has unzipped that. And if you want to come up in a minute, you can play with it. It's got kind of sharp edges. But so there's a layer of this nitronic faulty steel, which is some of the world's strongest steel. Then there's another coil. Then there's about 1 inch of 4 layers of copper. Then a small gap so we can get liquid nitrogen in there to get it cold, make it stronger, better conductor, like the tube got better when it was cold. Then more. And so basically, when you look at this cross-section, it's about 2.5 feet of solid copper and reinforcing material. So it's like Russian doll, coil inside coil inside coil. The innermost coil, which has sort of got this green color here, is the bit that has the highest stress. This is the bit that in this figure gives us the little kick up to 100 Tesla. This piece is designed to be the piece that fails, and in fact we're already on our 3rd or 4th, we call it the insert part of the coil, because that has the highest stress. What's quite incredible is that we can fail one of these without propagating this to a huge detonation. And so that really speaks to quite incredible engineering, and the fact that working in Los Alamos, you have access to some great engineers that can design the system. But these things will eventually, they do fatigue, they do stretch the conductor, the reinforcing shells do eventually break. So.
At some point, we have the power grid now.
Mm-hmm.
We lose like 6 to 8%.
Yeah.
Does anybody envision a superconducting material being strong in the current towers?
So I think New York City has already invested in some superconducting transmission lines, though what they basically have to do is have equivalent to one of these thermos flasks to keep liquid nitrogen temperature around the conductor at all the time while it's carrying the current. And so that's a significant infrastructure cost to keep it cold. We don't know the sort of lifetimes and fatigues that happen there. Again, they're ceramic materials. So let me get one of these out. You can see these aren't ductile materials like copper. These are hardened ceramic. So it's like trying to make a wire out of your cup. That's not an easy task. You can't draw it. It's not something that's bendy like copper. So there's all sorts of challenges, not only to go from something that superconducts at 100 Tesla and carries a huge current density before you destroy superconductivity, but physically making the wire. And one of the things that we've discovered is that in following the recipe of saying that we can find superconductors close to this sort of magnetic insulator, we've been able to find other families of superconductor that are actually somewhere in between. They still have some of the ductile metallic properties that you can make wires from, but still have rather high critical currents and critical magnetic fields, and so might have, although not have quite as high a transition temperature, might have better industrial application. But again, something that we've discovered in the last 5 years isn't necessarily going to see a technological application for the next 5 or perhaps even more.
And then on the power transmission line, at either end, there's what's called a damper to counter some of the vibrations.
There are numerous, even making connections between 2 superconducting wires is a challenge. So it's not like taking a wire nut and twisting it onto 2 copper wires.
Thank you so very much, Ross.
No problem.